Hello everybody and welcome to our third lecture in the optical system course. Today we are going to continue what we started in week 5, lecture 3 under the title of atomic radiation. If you remember, we start about talking about what's called an hypothetical model for a black body radiation. We say that the black body is a body where there is no reflection, no transmission, 100% absorption, and 100% radiating isotropically. So, we say that our lecture will be provided either through the reference laser electronics, which is by um, um, Verdine chapter 7, or you can visit any additional sources either using MIT open courses or any other additional source. Okay, let's now go to this equation. We say that this equation is an empirical equation to demonstrate the density or the density of radiation for a black body radiation in function of mu, which is the frequency, or you can turn it to be in function of lambda, which is the wavelength. This equation expresses that by each radiation, or depending on the temperature, the radiation can have different colors, as you can see here, starting from going to the far infrared till you can go to the visible, and then you can go to the ultraviolet depending on the temperature of radiation. Then we turn to Einstein idea. Einstein starts with assuming that for any two energy levels, any two successive energy levels, we have to we have to think about the different probabilities for electron and photon motion. Before Einstein starts to make his assumptions, we can easily say that if we have two energy levels, then we have two probabilities. The first probability is an electron to a photon that can be captured by electron. The electron is in the valency band. The electron will capture a photon. The photon energy should be E2 minus E1 is greater than EG. So this photon this electron will transfer from the valency band or from the E1 to the E2. And this process we can call it the absorption process, because in this case electron absorbs the photon, as you can see. The second idea is the reverse idea. When a photon in the E2 band, in the higher band, fall to the E1 band, and this transfer of energy is transferred to a photon with an energy E2 minus E1. So we call it emission. So again, before starts Einstein principles, here we can say that for two energy levels we have two probabilities. Either the photon to be absorbed by electron and the electron transfer from the E1 to E2, or electron fall from E2 to E1 and emit a photon with an energy E2 minus E1. When Einstein starts to think, he says that no, we have actually three probabilities, or in other words, we have finite number of probabilities. However, we will concentrate only on three probabilities. Let's now start to demonstrate these three probabilities and write a rate equation for each of these three probabilities. The first one is, we call it the spontaneous emission. We have an electron in the E2 band, E2 energy level. This electron will start to lose energy due to scattering or collision or whatever it is. So the electron will lose energy and will transfer from E2 to E1. In this case, as far as the electron is transferring from E2 to E1, a photon will be emitted. The photon energy is E2 minus E1 basically. However, there is no restriction about this photon regarding the direction or the polarization. So this photon can be emitted in any direction, or this photon can be emitted in any or with any polarization, either S polarized or P polarized. This is what we call a spontaneous emission. Now we are trying to write an equation to express the rate of population in either E2 or E1. Here we are talking about the rate of population in terms of the number of electrons. So when we are talking about the level E2, as far as the electron will leave E2 to E1, then the population in E2 will decrease. That's why the term dN2 by dt, which expresses the rate of population of the energy level number 2 with respect to time, it will have a negative sign because the rate of population will decrease. This rate of population will decrease with a rate called A21 with respect to N2. For example, you are losing 1 electron per second. So in 10 seconds, you will lose 10 electrons. Or in other words, if I say that you are losing 1% of your electrons per second, 1% of your electrons per second, then after 10 seconds, you will lose 10% of the electron you have in N2. So you have to multiply 10%, which is 0.1, times the number of electrons of N2. For example, they have 500 electrons, then the total amount of electrons you will lose is 0.1 times 500, which is 50. So that's why we are multiplying 81, which is the rate, multiplied by the number of electrons in N2, which is the source where I am losing. And as far as you are losing electrons, then we have a negative sign, and again we call this spontaneous emission. Let's turn to the other process, which is absorption. Now we have a photon. This photon will be absorbed by an electron, but there is here a constraint, there is here a condition, that this photon should have an energy equals to or greater than E2 minus E1. Otherwise, this photon will not be absorbed. So, electron will absorb the photon, electron will transfer from the energy level E1 and will go to the energy level E2. In this case, the energy levels, the number of electrons in the energy level E1 will decrease because you will lose electron from E1, and the number of electrons in energy level E2 will increase. That's why when we write the term dN2 by dt, which expresses the rate of population in the energy level number 2, you will find it with a positive charge because here the number of electrons in the energy level E2 will increase. So it's a positive. Again, we use the rate. Here the rate is named by P12, and then we are talking about N1 because we are taking electrons from N1, so N1, and a new term which is rho V is added. This rho V is added because rho of mu is added because this process is dependent on frequency. Again, this photon will be absorbed only if and only if the energy of this photon is E2 minus E1 or greater. Otherwise, the photon will not be absorbed. So this process is dependent on frequency. Not any photon passing the material will be absorbed. Only those with energy E2 minus E1 or greater. However, if we return back to the first process, we find that this process is independent on frequency. That's why you will not find the rho mu term here because it's an electron leaving energy 2, going to energy 1 and emitting a photon. No condition here. There is no condition here. However, in the second case where we have the absorption B12, there is a condition that E2 minus or the photon should have an energy E2 minus E1. Okay. Now let's go to the third, which is the most important case, what Einstein called stimulated emission B21. In case number 1, when we have a spontaneous emission, we are talking about an electron who left E2, transferred to E1, and emitted a photon with an energy E2 minus E1. The emitted photon has no restriction about either the polarization or the direction. Now, we have another condition. We are talking about actually another story. What if you have an incident photon of an energy h mu equals to E2 minus E1? However, for some reason, this photon will not be absorbed. Additionally, and by chance, in the same time, electron will leave the energy level E2 and will go to the energy level E1. And will emit a photon. So, you have an incident photon equal H2 minus equal H mu which is equal E2 minus E1. And now you have another photon due to the process of transfer of the electron from the energy level E2 to the energy level E1. Then you will have two photons by the end of the day. A first photon is the initially incident photon, and a second photon due to the process of the electron transfer from E2 minus to E1. But that's not only the case. There is another condition, that the two outgoing photons should have the same polarization and the same direction. Of course, they have the same energy because the incident one is with an energy E2 minus E1, I already mentioned, and the second will be automatically equal to E2 minus E1 because it is emitted due to the transfer of electron from E2 to E1. So they should have the same energy, the same direction, and the same polarization. If this happens, Einstein calls this process as the stimulated emission, or the P2. Now, in order to write a rate equation for E21, we will say that E2 will lose electrons, so dN2 by dt will be negative. Again, because you are losing electron will transfer from E2 to E1, so E2 will be negative. B21, which is the rate, and then you are losing electron from N2, that's why we multiply by N2. And again, this process is a frequency dependent process because, as I mentioned, the incident photon should be with an energy E2 minus E1, and the one going surely will be with an energy E2 minus E1. So this is a frequency dependent process, that's why we have the term rho. So as a summary, we have three possibilities, or again, we have finite possibilities, but we will concentrate only on three. The first is an emission process with no restriction, where we call it the spontaneous emission. A photon is emitted. This photon can have any direction, can have any polarization. A second is an absorption. It's a frequency dependent process because the absorbed photon should have an energy E2 minus E1 or greater, and by the end of this process, electron will transfer from E1 to E2. A third process, which is a stimulated emission. It's actually a mix between the first and the second. We have an incident photon again, like the second. However, this photon will not be absorbed. And we have an electron which is transferred from E2 to E1 as the first. However, there is another condition, that the emitted photon and the incident photon both should have the same energy, the same polarization, and the same direction. If this happens, we will call it stimulated emission. So this is the three processes. Naturally, the three processes will happen simultaneously. So we can write a general rate equation. The first term representing the spontaneous emission, the second term representing the absorption, and the third term representing the stimulated emission. Of course, you can easily imagine that dN2 by dt equal negative dN1 by dt. So what you will lose from energy 2, you will gain in energy 1. What you will gain from energy 2, you will lose from energy 1. That's why they have negative direction, negative sign. Now we have an equation, but this equation is mathematically called the differential equation because it includes a differential term which is dN by dt. In order to simplify this equation a bit, we can assume what's called a steady state. When you assume a steady state, this means that dN by dt is equals to 0. Actually, this is a very important note. Here we are talking about what we can call a thermodynamic equilibrium. In thermodynamic equilibrium, we have to notice that that means that there is no electron motion at all. However, there is electron motion, but the equivalent is equal to 0. That means the number of electrons leaving E2 to E1 equals to the number of electrons leaving E1 to E2. So the net rate of a change is equal to 0. However, there is a rate of a change, or however, there is some sort of motion. So simply, if you assume equilibrium, again thermodynamic equilibrium, you can say that dN by dt is equal to 0, and then you will have an equation, a linear equation is equal to 0, and then you can write these terms that n2 over n1 equal these long right-hand term. Now, let's turn to Planck. Let's turn to Max Planck. Planck says that whenever you have energy level, or first let's say that Planck says that electrons exist in discrete energy levels. So, for example, if we are talking about these two levels are at discrete energy levels. I mean, there is no possibility for an electron to occupy an intermediate level between these two levels. And the energy level of these energy levels is nh mu. I mean, if the energy level of this energy level is nh mu, then this one will be n plus 1 h mu. So simply, and using the Boltzmann statistics, I think we described it better in the lecture in week 5 if you remember, we can say that n2 over n1 equals to g2 over g1, which is our some constant, not out of scope for our course, e power minus h mu over kt. And we recently reached that n2 minus n1 equals to this long term. So we can easily say that g2 over g1 e power minus h mu over kt equal this long right hand term. Using this equation, you can find an equation for rho of mu that's equal this huge term. Of course, this equation will not be asked to be memorized for you. So, what is interesting is this equation is that this equation is typically the same trend like the black body radiation equation I showed in the beginning of the lecture. So, from the analogy of these two equations, you can find the relation between the coefficients. I mean A21, B21, and B12. And the relation will be in this form. B12 equal G2, B12 times G2 equal B21 times G1, and A21 over B21 equal these two. Here I'm not so interested in mathematics, but I'm interested in concepts. Because by this analogy, Einstein have proved that these three equations, these three phenomena, or these three coefficients are somehow correlated. When we describe these three processes, we think that they are actually three independent processes. But based on this proof, he proved that these three processes are three correlated processes. Now, let's turn to another point in the same lecture. Again, I believe that all these parts were already delivered in week 5. However, I just re-deliver it in order to memorize together what happened in lecture number 5 or in week 5. Einstein starts to build his theory knowing that we have two discrete energy levels, energy level number 1 and energy level number 2. Now, what if we have energy bands instead of energy levels? When you have energy levels, then it's crystal clear. When electron move from E2 to E1, then basically it will emit a photon with an energy E2 minus E1. No other possibility. However, when an electron leave energy band number 2 and go to energy band number 1, here we have more than one possibility, because it may left from this higher energy level and go to a very lower energy level like this described. So the emitted energy will be greater than E2 minus E1. Or it may left the lower band in energy band number 2 and go to the higher band in energy level number 1. Then the emitted frequency or the emitted energy is low. In this case, you don't have a discrete possibility for energy emission. Actually, you have a series of possibilities, series of probabilities for energy emission. That's why we have what we can call a line function. Now, this is a very important function that you should understand very, very, very well. It's actually somehow a function that you will have to see in any final exam in any optical course. It's a function that describes the probability of finding an electrons, or the probability of finding photons at different frequencies. So, at the frequency mu node, which is E2 minus E1, you have the maximum probability. However, it's not the only probability, because there is some probability to find photons with an energy greater than mu node, and there is some possibility to find an a photon with an energy also smaller than mu node. By the way, this is just an example for the line shape function. Line shape function can have different mathematical trends based on the system. Actually, we will consume a huge amount of time either in the lecture or in the tutorial in order to study different shapes or different trends for the line shape function. However, there are two important notes. I would highly appreciate if you give your focus now on these two very important notes. The first note is that this is a probability. So, the summation of this probability should always be equals 1. That's why the integration of any line shape function from 0 to infinity should always equals to 1. Again, it's a probability. The summation of probability is equal to 1. That's why the summation of any line shape function should be equal basically to 1. This is the first important note. The second important note is the y-axis. The y-axis is a probability. That's great, but it's a dimensionless, or it has some dimension. Here we think about it. You say in this equation, I believe you trust this equation, that the summation of probabilities is equal to 1 all the time. So, you say in this equation that when I multiply g of mu times d mu, the results will be equals 1. Okay, 1 is a dimensionless, 100%. So, the multiplication of these two parameters should result a dimensionless unit. We know that d of mu is a frequency unit, so it has a frequency of 1 over second, or hertz. That means that g of mu should have the reciprocal unit in order to have a multiplication equal to 1 or dimensionless. I mean, if this hertz, if d mu is hertz, then g of mu should be 1 over hertz or seconds. So in this case, g of mu, which is the y-axis, have a unit of seconds to have a multiplication equal to 1 or dimensionless. Now, is this the only shape to find a line shape function? I mean, is this the only way to plot a line shape function? Actually, the answer is no. Because, as you know, we can express the photon by mu, that's true, which is frequency, and we can also express the photon by lambda, which is the wavelength. So, you can find a graph representing a line shape function, and in this graph, you will find that here we have an x-axis of lambda, here we have d lambda, and here we have g of lambda. And in this case, the x-axis will have a unit, for example, meter, and g of lambda will have a unit of meter minus 1, because it has a reciprocal, or 1 over the unit. A third case, you can have this this x-axis with an energy, electron volt. So you can have here dE, and you can have here g of E, and in this case the unit of g of E will be 1 over electron volt. So the x-axis for a line shape function may be frequency, may be wavelength, may be energy, and in each case the y-axis will have a unit 1 over the unit of the x-axis. So if it's hertz, then you have 1 over hertz, which is second. If it's meter, then 1 over meter, meter minus 1. If it's electron volt, then it's 1 over electron volt. All are possible cases for a line shape function. Okay, now Let's turn back to the rate equation in its general form. If you remember some slides ago, we say that we will somehow simplify it by assuming that it's under equilibrium, and we say that dN by dt is equals to 0. And we solve it to get rho of mu, and we use rho of mu in order to get a relation between the Einstein coefficients, and we did. Now let's do it in another format. Let's return back to the general form, the differential equation form, the general differential equation form. But here we have to think twice. Now, in the previous case, we said rho of mu, because we say that we have a frequency dependent condition, which is rho of mu. However, based on this slide, we say that, oh, now it's not only rho of mu, we again also have a g of mu. So, what we are going to do now is that we will replace each rho of mu by rho of mu, g of mu, d mu, and we call it mu dash as a dummy parameter in order to get a function of mu. For the first term, which is, if you remember, a frequency independent term, you will find that we have integration from 0 to infinity g dash of mu d mu dash, which is basically equals to, equals to 1. This is a very simple integration, because as you know, the integration for a line shape function for a probability is basically equals to 1. So this integration is equals to 1. Now, so you don't have this integration. However, in the other two terms, which is the absorption term and the stimulated emission term, we have this integration. But let's wait a bit and ask. Here, this integration is equal to 1. This is an easy integration. But here, we have no idea about g of mu. We know that the g of mu is a probability function, and its overall integration is equal to 1. But we don't know specifically what g of mu is. It may have different types of mathematical functions. And also, we have no idea about rho of mu. It's just a function of frequency. But how it looks like, we don't have an idea. Let's start with rho of mu. Rho of mu may be a black body. If you remember the first slide, we talk about black body, and then we plot this curve, and then we write this equation, and we say that, oh, this is the radiation from a black body. So rho of mu may be a black body. I mean, the body which is emitting the photons is a black body. So we may have a rho of mu like that. Or this is one of the extreme cases. A black body, it's a body that radiates photons with different type of frequencies. As you can see, here you have infrared photons, you have a visible photons, and you have also an ultraviolet photons. So you have photons everywhere with different frequencies. This is the case. So your rho mu, your source of photons, may be a black body radiation. But this is actually the most difficult case. Is there an easy case? Yes. What if your rho of mu is a laser? What is laser? Actually, we don't know a lot about laser up till now. But laser, we can say easily, laser is a monochromatic source. Or in another simpler format, it's a single wavelength source. I mean, if you would like to plot the spectrum or the variation of frequency for laser, you will just plot this, what we can call impulse, or a delta Dirac. If you remember the delta Dirac, this is delta Dirac, because laser is a source that emits photons in a single frequency, as you can see here. So your rho mu may be a very wide source like a black body, or maybe an absolutely narrow source like a laser. For a very easily mathematical implementation during this course, we will assume all the time that our rho mu is a laser. So you can simply say that rho of mu is a delta Dirac function at any certain wavelength. This rho dash is depending on the wavelength of the laser. It may be red, it may be yellow, it may be blue, it may be ultraviolet, it may be infrared, but all the time it's a single frequency source. So you can say that in this case the integration will become that you will substitute each rho of mu by a delta Dirac function. If you remember from the communication, I believe you are a very good communication students. So if you remember from our communication, when you multiply a delta Dirac function times a function in the frequency domain and you make an integration, the output is simply the same function you are multiplying. So if you replace this rho of mu by a delta Dirac function and you insert the delta Dirac function in this integration, the output will be simply the g of mu, and then you will find this equation, which is the same. Typically rho of mu now is just an amplitude, as you can see here. Rho is just an amplitude representing the value of the delta Dirac function, that's all, and the only function of frequency is g of mu, which is the line shape function. So this is the simplest format, but please remember that this equation is written based on the assumption that rho of mu, or the light source, is a laser single frequency monochromatic source. Now, knowing that equations that B21 equal B12 G2 over G1, please remember that we already drive this from the Einstein relation when we use the analogy between this equation and the black body radiation equation, and we get these two relations. So we are using now these two relations in order to make our equation function in only one coefficient. And here we are using the term that the density is only the intensity divided by the velocity. You know that the velocity of photon is equals to c divided by the refractive index of the medium, which is n. So if this photon is propagating in air, it will have a frequency, it will have a speed of c. If this light is propagating, for example, in any other medium, for example in water, then the velocity will be reduced by a factor root epsilon r, or refractive index. So we have I mu over c over n, which is I is the intensity and c over n is the velocity. And by all these substitution, very too much mathematics, we don't need it a lot actually, you can reach this equation. Please here have a look on this equation. This equation says that dN2 by dt, which is, if you remember, the rate of population of the energy level number 2, how many electrons are leaving and how many electrons are coming to energy number 2. We say that this is due to three processes. The first process is the spontaneous emission process. The second process is the absorption process, and the third process is the stimulated emission process. This is a too long equation. Okay, now let's focus on this equation a bit. Again, you can find here that the tag very important. Please don't forget, you are not asked to memorize all these long mathematical equations. Actually, by the end of this lecture, I will solve with you one of the problems that we usually see in the final exam or the intermediate or something like that. Okay, so now we have these three terms, but let's now focus a bit on this middle term. A21 lambda square 8 by n squared g of mu. Actually, this is a very interesting term. What if I ask you, what is the dimension? What is the unit of this term? Oh, let's start with the easy terms, not the tough one. 8 is a dimensionless, pi is a dimensionless, n is a refractive index, is a dimensionless. So all this denominator is dimensionless. Lambda is wavelength, so its dimension is meter. Lambda square, then it's meter square. Simply like that. So G of mu, I think we spend a lot of time about G of mu. We say that, okay, G of mu is a y-axis of the line shape function, and it should have a 1 over the dimension of the x-axis. That x-axis is a frequency, hertz. So G of mu will have 1 over hertz, which is second. So simply G of mu is second. Should be like that. So G of mu is second. So what about A21? What is the dimension of A21? Oh, A21 has a dimension or not? Now let's turn to the first equation where we see A21. Okay, it was this equation actually. We say that N2 by dt equals A21 times N2. Let's make it. Right hand side dimension should equal to the left hand side dimension. Very easy like that. So the right hand side or the left hand side dimension has an unit of electrons, number of electrons, N2 over second. So electrons over second. Here we have N2, which is electrons. So this A21 should be 1 over second, so that we have an equivalent or a compensated equation. So the dimension for A21 is 1 over second, which is actually makes sense. If you remember, I say to you an example. What if I am losing 0.1% of my electrons per 1 second? So I should use the term per second. What if I told you that 5 people dies with coronavirus? I think your next question is, what is the time interval you are talking about? 5 people dies per day, 5 people dies per month, 5 people dies per minute. So in order to define any rate, it should be over a time interval. That's right. So A21 should be usually over a second. So let's now return to the equation. And we have, I'm sorry. Let's now return to this equation where you can see again 8 by n squared is a dimensionless. G of mu has a dimension of second. A21 has a dimension of 1 over second. So A21 by G mu is a dimensionless again. Then the dimension of this whole term is simply meter square. That's why we call this term as the stimulated emission cross section, as if it's an area, and we call it the term sigma because it has a unit of area, it has a unit of meter square. That's why we have to be extremely focused on this term because it's actually a very important term. Now I just rewrite the equation with dN2 by dt equals minus A21 N2 minus, I remove all these huge terms and I put sigma I mu over H mu N2 minus N1 G2 over G1. This is the rate equation again. I believe you can still ask yourself why we are doing all these stupid mathematics, why we are doing all these stupid equations, all these too long equations. Now let's do an experiment. Okay. Based on what we were doing in the previous lecture or in the previous maybe 38 minutes, we are talking that there are 3 main possibilities when you have 2 energy levels or when you have 2 energy bands. There are 3 main possibilities for photon either emission or absorption. Now we say that, let's now return to the Einstein coefficient again, please. We say that we have 3 cases. The first is electron moving from E2 and going to E1 and emitting photon. It's okay. And the second is a photon is coming to the material, absorbed by electron. The photon has an energy E2 or minus E1 or greater, so the electron will absorb the photon and will go to E2. The third is you have a photon coming. This photon will not be absorbed. At the same time, electron leave E2 and go to E1, emit another photon. Both photons have the same energy, the same polarization, the same direction. But you have here to stop and ask yourself the question. In case number 2 and in case number 3, you assume that we have an incoming photon. From where should we have this photon? We should have somewhere a light source here. We should have a light source here. So this light source emits photon and this photon reaches the material. So our experiment that we will do it in part 2 of this lecture is a very basic important experiment. It will be a setup like that. We will have a light source. We will have a material in between, and then we will have a detector. We will measure how many photons will be emitted by the current source, by the light source, and how many photons will reach the detector. And we will ask ourselves, does the number increase or decrease? If this number increases, that means you have a light amplification. You amplify the light. We insert one photon and we get 2. Again, please remember, we insert one photon and we get 2. If you remember, we say this word when we are talking about the stimulated emission. We are inserting one photon and then we get 2. So, if you have a stimulated emission, or if the stimulated emission is dominating, then the number of photons should increase. But if the stimulated emission is not dominating, then you will have either an absorption, which means that the number of photons will decrease, or we will have a spontaneous emission, which means that you will emit photons, okay, but these photons will have different directions and will not be detected by the detector. So, in the next lecture, or actually in the next part of this lecture, we will focus on this setup. How we can guarantee that we have a dominating stimulated emission. How we can guarantee that we have a dominating amplification. After that, we will solve a very important example about the line shape function, which will be the termination of this lecture. Thank you very much and see you in the part 2 of lecture number 3, which is atomic radiation.